Good afternoon, students, and welcome to today's lecture. Today we're going to be talking about aerodynamics. So, could please everyone go on mute? I think there's still a few not on mute yet. What is aerodynamics? Why are we talking about this topic now? Well, aerodynamics is the study of flows, fluid flows, mostly air flows, that's where the name is coming from. Air flows around solid objects. Solid objects, such as in this picture, a wing, for instance. And the result of aerodynamics typically is a prediction of the lift force and of the drag force. Right? We have talked about lift and drag a few times already, but now we're going to try to apply it to objects in an airstream, in a fluid stream. And that is the topic of fluid mechanics, of aerodynamics. So what are we going to talk about today? We're going to talk about lift and drag. We're going to define it first, and then we're going to look at drag coefficients. Mostly, we're just going to look at a few examples, so you start understanding what these drag coefficients mean, how we can interpret them, and how we can put them in relation to what we have learned so far. Then we're going to look at a bit more at where the drag is coming from, and we're going to split into friction drag and pressure drag. We already did this quite shortly in the context of Stokes flows, so we're going to go back to that. And then we're going to talk about a very special phenomenon. It's called the drag crisis, and it's the drag crisis of a sphere mostly. It also exists for cylinders, and you will see that it has is quite relevant, especially to sports ball aerodynamics. So like golf balls, but also soccer balls. We're going to look at cricket balls and so on. And then finally, the last topic will be a little view or glimpse at airflow theory. Airflow theory by itself is a rather large topic, and there are special lectures on that. But I'll try to give you some ideas which direction this will be. Okay, so let's start off with the definition of lift and drag, and to this end we use this diagram here. You see an airfoil with flow coming from the left with a velocity u, and we have learned now with many different concepts how the streamlines will shape around this object, and you probably have some imagination what this could look like. We also know that the airflow around this object will create local pressure forces onto the object, and it will create local shear stresses onto the object. Maybe I draw this quickly on a diagram so you can see that. So we have our airfoil here, and we have a flow with velocity capital U coming from the left. I'm using blue for streamlines. The streamlines are likely to shape something like that around this airfoil. And on the surface of this airfoil, we'll find pressures. And these pressures, by definition, are perpendicular to the surface. And they will change. The pressure force will change as we go along the wing. We have already looked at this in the context of potential flow, for instance. And because we're looking at the viscous flow, one color here, because we're looking at the viscous flow, We'll have boundary layers on the surface of this wing. What they could look like, something like that. Boundary layer here. And due to the velocity gradient, we get a tangential shear stress. And these shear stresses, they may be higher or may be lower. They will be on the bottom and everywhere. So we have a distribution of normal pressures and of shear stresses on the surface of our airfoil. And of course, we can add up the contributions of these tangential shear stresses and the contributions of these pressures, and we obtain a resulting force. And that resulting force, we call green here, will be a vector pointing, well, maybe in this direction. It could also be in another direction. So F is the sum of all contributions of all shear forces and all pressures that we can compute with the different tools that we have learned so far. Now, what is lift and drag? Now, lift and drag is just a decomposition of this force vector into its two components. And this is really an arbitrary choice. And that arbitrary choice means that we take one axis in the direction of the oncoming flow, and one axis perpendicular to that. Could also be different, but this is a choice that someone made probably 100, 150 years ago. And they said that the component of this force vector going into the direction of the oncoming flow is called the drag force, and the force perpendicular to it is the lift force. Both are vectors. Okay, so this is how lift and drag are defined. It's the decomposition of the resulting force vector. And this is really what the diagram on our slide is showing. We have a resulting force F decomposed into a lift and a drag force. On the bottom of the slide, you have two formulas, and these are formulas, or at least the first one, that we derived in the very first lecture of this course. That was the result that came out of Buckingham pi. There, I think we did it for a sphere, but I also told you that this whole Buckingham pi derivation works for any object, in that case, an airfoil. And that result said that the drag of such an object divided by this quantity, 1/2 rho u squared times a, where a is an area. I will talk about this later on, what this area exactly is. That this ratio is a non-dimensional quantity, and that we typically denote it by the variable CD for drag coefficient. Or in German, you so often see CW for Widerstandsbeiwert. And you can do the same story, of course, also for the lift, and you get the CL, a lift coefficient. And both coefficients are non-dimensional, but they're not constant. Both are functions of the Reynolds number. That was also a result that came out of Buckingham pi. So if we have a certain shape of an object, like the geometry of this airfoil, no matter how large it is, no matter what the oncoming flow velocity is, no matter what the density of the fluid, the viscosity of the fluid is, there is a unique, or there is a drag coefficient which is uniquely only a function of the Reynolds number. So if we know that drag coefficient, we can compute the drag for that particular situation. So there are handbooks full of drag and lift coefficients. We were going to focus on drag coefficients now. So this is such an example out of a book, a list of drag coefficients for a bunch of, let's say, very simple geometries. Top left, you have a flow or the drag coefficient for the flow along a cylinder, flow going the axial direction of the cylinder. You have different L over D ratios, length over diameter ratios, and you see back here the drag coefficient. And there's this cross-section A, which must be defined. It's a matter of definition what we want to choose. In the case of these coefficients, the 0.91, 0.85, and so on, they chose this cross-sectional area, which is essentially the area of the cylinder cross-section of the circle generating the cylinder. We have a same thing for flow perpendicular to a cylinder, and so on, and for a board, for the tilted board. And let me actually go back to this one. I would now like to point out what we have on the bottom right. This is more a practical, technical application. These are drag coefficients for cars. And again, for cars, we need to define what do we use as a cross-section. And you see it here in this diagram, the convention, and it's really a convention, the convention is to use the projected area. If you look at the car in axial direction, the whole projected area of the car is this coefficient, or not the coefficient, it's this number A, this area square meter, okay? So we have to be careful. If we have a drag coefficient, it needs to be multiplied by 1/2 rho u squared, being the velocity of the car, times the cross-section of the car. That is often forgotten. Let us take a quick look at this link down here. This is a Wikipedia page. I need to change the, yeah, here. I hope you can see the Wikipedia page now. It has a nice list full of drag coefficients of cars, right? You have here the names of the cars, and you have here the drag coefficients of the car. Like very high drag coefficient, you see that here, for instance, a Hummer car, yeah, one of these cars has a high drag coefficient 0.57, and some sleek car, well, let's take here this Lamborghini Diablo, has only 0.31 drag coefficient. And sometimes when you look in a newspaper ad for a new car, sometimes depending on the oil price, sometimes they make advertisement with a low drag coefficient. However, I hope that with what I just said, the last 5 minutes, you can appreciate that a drag coefficient by itself does not tell the whole story. Let's look at an example what I mean. Let's take, which car do I want to take? Yeah, here. Here, this Lamborghini looks nice and sleek and very aerodynamic. It has a drag coefficient of 0.42. 0.42. I remember this number. Now let's scroll down a bit. And let's go to where we have it. Yeah, here, the Dodge Durango. Big SUV car, certainly not the best example of low consumption, low drag. probably all of you, if you compare this Lamborghini and this Dodge Durango, you'll probably say, well, Lamborghini has less drag, and that's of course true. However, if we look at the drag coefficient, we're at 0.33. So it has a lower drag coefficient than the Lamborghini. And of course, we know now that because in order to compute the actual drag, the drag force in Newton, we have to multiply this drag coefficient with the area, with the projected area of the car. And of course, the Dodge Durango has a lot larger area than the sleek, thin Lamborghini car. So be careful when you only look at drag coefficients and try to make statements about the drag of an object. It's certainly a good quantity for us as engineers, but if you want to make some marketing statements, it's a bit dangerous. Okay, let's switch back to our table of drag coefficients and let's go forward. Just want to make an example. So in this table here, I have highlighted one drag coefficient, and it's the drag coefficient for the L/D ratio, so it's the aspect ratio of the cylinder going to infinity. So what does that mean? Essentially, this is an infinitely long cylinder with a perpendicular flow coming onto it. So it's like a 2D situation. It's like a two-dimensional, infinitely long cylinder. And that has a drag coefficient of 1.2. This is what you find in such books. Now, another word of caution for that. We know from Buckingham pi that drag coefficients are not just single constants, but are in reality functions of the Reynolds number. So if this table were completely correct, it would say it's 1.2 for a certain range of Reynolds numbers, or maybe for a certain Reynolds number. And to this end, please look at this diagram on the bottom right. This is the diagram telling the full story of the drag coefficient for the flow around a cylinder. And in the red line, I marked this value of 1.2, and we see that indeed in a range of Reynolds, let's say about 1,000 to about 10 to the 5, 100,000, or maybe a bit more, in that range, 1.2 is indeed a good approximation to the actual drag coefficient. We see that for very low Reynolds numbers, the drag coefficient is much higher and actually decays with Reynolds number. This whole story about Stokes flow, right? I mean, Stokes flow was for a sphere, not for a cylinder, but the story is similar for a cylinder. Okay, so in this range, the Stokes flow range, 1.2 is actually not a good value. And there's this kink here. We're going to come back to that. This is called the drag crisis, where the 1.2 is also missing. So again, always keep in mind when you look at these tables, if you find a number for the drag coefficient, it's specifically only drag coefficient for a certain Reynolds number, or let's say a certain range of Reynolds. So let us continue and try to understand a bit more where this drag is actually coming from. These are two pictures we had in previous lectures, most in the context of boundary layers and of the potential flow theory. Right? We see here on the left a schematic, again, of a flow around an airfoil, where we see illustrated the boundary layer, and we see our outer flow solution. And you should remember that the boundary layer is actually very good to predict the local shear forces, and that the outer flow solution is actually quite good in predicting the velocities in the outer flow field, at least on the windward side, on the upstream side. And from these, we can also compute the local pressure forces. So if we look back at our blackboard, the pressures, the yellow pressures, are quite well predicted by the potential flow theory, and the red tangential shear stresses are quite well predicted by the boundary layer theory. Now, the thing that we call friction for a drag, so the drag due to the friction, I think that should be quite obvious. This is the drag exclusively due to the tangential shear stresses. So on the blackboard, it was the red or orange tangential shear stresses, which only comes due to viscosity, and potential flow theory, which does not have any viscosity in it, completely neglects that stuff. So that is the friction force. That is one contribution, sorry, friction drag, and that is one contribution to the total. So what about the pressure drag? Well, the pressure drag, it's a bit more complex, and neither potential flow theory nor boundary layer theory tells us the complete story of the pressure drag contribution. What we need to understand is the picture on the right-hand side. And the picture on the right-hand side shows flow separation. And the flow separation is actually a point where the boundary layer solution, a boundary layer on the upstream side along the wall, is detaching from the wall. And we get this large thing, which is typically called a wake. And in many cases, not always, but in many cases, is a turbulent wake. It's a wake with turbulent flow in it. The velocity conditions, or let's say the flow conditions in this wake, are very much different from what we had if the boundary layers were to remain attached all the way to the trailing edge of the sphere. So let's try to understand what is happening with the pressures in this wake. Or maybe let's first take a look at the pressures at the leading edge of this object, of the cylinder. Well, if we're sitting on the streamline directly in a symmetry plane of the cylinder, the streamline will end at the point that is also known as the stagnation point, because this is exactly on the symmetry point, the velocity will go towards zero. And Bernoulli's law, you remember Bernoulli's law, something we did quite early, I think third or fourth lecture. Bernoulli's law tells us that on a stagnation point, all the kinetic energy from the oncoming flow is translated or transferred into an increased pressure. So we have here a peak pressure at this stagnation point, which is equal to 1/2 rho u squared. And that's one of the primary results of Bernoulli's law. So the pressures here at the leading edge of this object are quite high, and they're pushing into the object. So maybe let me draw this on the blackboard again. So we do have our cylinder here, and we have our oncoming streamline, the one in the center, creating a stagnation point, and some other streamlines going around, and so on. So the pressures here at the leading edge, they will be quite large, and they will be highest right here at the stagnation point. So this is pressure pushing back. And of course, on the backside, there will also be pressures. In the case of potential flow, where the flow was fully symmetric and we did not have any losses due to viscosity, the velocity field was fully symmetric, and the pressures here were of equal magnitude, just in opposite direction, right? And that's why in potential flow, the two pressures cancel each other. What is happening now with the flow separation, here at the separation points, we get this turbulent wake. And instead of recovering, we have here locally, because the flow is accelerated, we have locally pressure minimum, and in potential flow, the flow is decelerating again and coming to a halt here in potential flow, so we have again a pressure maximum. But in this wake, the flow is not completely decelerating, so the pressure cannot recover its large magnitude. So we usually have a much lower pressure back here in the wake, or in some cases, we might even have a negative pressure with some suction. We see this later. But the main message is the high pressures here on the leading edge, they are not counterbalanced by high pressure here. Here in the wake, the pressure is typically much lower than the pressure on the upstream side. So we're pushing here hard and we're pushing here only a little back. So in total, we create a drag force D, and I put a lowercase or an index P to indicate this is a contribution only from the pressure difference. This is the pressure drag contribution. Has nothing to do with viscous friction forces. I mean, indirectly, yes, because flow separation, all that, but in the first place, this drag comes only due to pressure differences upstream versus downstream. I'll switch back to the slide. In general, just as a rule of thumb, you could say the bigger the wake is, the more wake we have, the more the contribution, or the bigger the contribution of the pressure drag, and the smaller the wake, the more the contribution of the friction drag counts. Let's look at the following diagram, the following slide. What do we have here? We have a comparison for 4 different objects of the contributions of pressure drag and of friction drag to the total drag. So in the first example, where it's just a flat plate and nothing else, there is no wake. There's no wake because streamlines are not really displaced, maybe just a little bit displacement thickness of the boundary layers, but that's it. So the only drag this object can experience are the tangential shear forces of the viscous friction in the boundary layer. So this is why in this example, we have 100% friction drag and 0% pressure drag. The bottom example, where the plate, instead of parallel to the flow, is now perpendicular to the flow, is the exact opposite. Friction drag has 0 contribution to the total drag. Well, you might wonder if there's no boundary layer here at the upstream side of the plate. Yes, there is, but because the plate is perfectly perpendicular, the shear stresses will be perpendicular to the oncoming flow. So if they can create anything, they would certainly not contribute to the drag because drag is only parallel to the main flow direction. Okay, so the only drag that we see in this flat plate is due to pressure drag. It's due to this huge difference between the pressures on the upstream side, which are high because we have a stagnation point on the upstream side, and the pressures on the downstream side, which are relatively low because we have a huge wake and the flow is certainly not coming to zero velocity. And then, of course, we have everything in between. And a typical airfoil, a well-designed airfoil, has relatively little pressure drag and a lot of friction drag. This is also why in an airfoil, if you want to reduce drag as an engineer, it's much more promising to work like on a very smooth surface, not to have any asperities on the surface so you can reduce the friction drag, whereas the pressure drag, if the airfoil is well designed and has no wake or only a very, very small wake, will be small anyway. And as soon as we go to a more blunt object, or sorry, not a blunt object, more of a cylindrical object, where the wake is not controlled and we create a larger wake, the pressure drag goes up and the contribution of the friction drag goes down. So let's see what this means for a cylinder. For a cylinder, I think we have seen this diagram. We have many different flow configurations. The flow configuration on the top left is the one that we looked at in one of the first lectures on Stokes flows. So this is where viscosity is dominating. We have symmetric streamlines, but it's not potential flow, it's the opposite, it's viscous dominated flow, but still the streamlines will look symmetric, but we have a lot of friction on the surface of the cylinder. At the same time, due to this friction, the flow loses energy. The flow loses energy in the sense of it loses pressure. So just due to this friction, the pressure here will be lower than the pressure on the upstream side. So we also have a contribution of the pressure drag. So in this configuration, this is the Stokes flow configuration. For the case, this is a cylinder, but for the case of the sphere, we noted that about 1/3 comes from the pressure drag, about 2/3 from the friction. If we increase the Reynolds number to range between 4 and 40, we see that the wake starts forming, but this wake is still a laminar wake. We have a separation point here, and we have a recirculation region. Certainly, the pressure here will be lower than it was in the previous case. So we increase in pressure drag. We have still the very high pressure on the upstream side, but a lower pressure on the downstream side in the wake. So still probably predominantly friction drag, but pressure drag has increased. And so the story goes on. The more we increase the Reynolds number, the bigger the wake becomes. And the bigger the wake becomes, the more the pressure drag has an effect, and the less influence or the less contribution the friction drag has. And the friction drag mainly comes from the shear stresses along the upstream surface, along where we have a nicely formed boundary layer with our velocity gradients at the wall, which create these tangential shear stresses. Reynolds 8 to 200, we still have a laminar wake. And this is what is called the Kármán vortex streak, this periodic change of vortices that are shed from the cylinder in opposite directions. Looks beautiful, but it's also still laminar. If we go to higher Reynolds numbers of, let's say, a few thousand, a few 100,000, up to 300,000 actually, we come into a situation where we have a fully turbulent wake. And we have a boundary layer, a laminar boundary layer, which happens to separate at the point which has been determined experimentally in many experiments, has been determined to separate at 82%. So at 82 degrees. So at 82 degrees, the boundary layer is separating from the surface of the cylinder, and we have a huge wake, which is turbulent. So this is a classical case where probably 90% or maybe more of the drag comes from the pressure drag, and only a relatively little drag comes from the friction here in the laminar boundary layer. This is, by the way, the configuration that we have. Remember maybe the first, or I think the third slide, with the drag coefficient of 1.2. Now this was in this range where the drag coefficient is approximately 1. Now there's a very special thing happening. If we pass this magic Reynolds number of 300,000, at 300,000, the boundary layer transitions from a laminar boundary layer to a turbulent boundary layer. Remember from last week, boundary layers can be laminar or they can be turbulent, and there's usually a critical Reynolds number for these boundary layers to transition from one to the other state. And for this boundary layer, this flow configuration, the Reynolds number, the critical Reynolds number, happens to be somewhere around 300,000. In the first place, if we were only to look at friction drag, transitioning from a laminar to a turbulent boundary layer would of course be negative, would increase the drag, right? Because the turbulent boundary layer usually has a steeper velocity gradient at the wall. Huh? Maybe you remember these diagrams where I showed you what a Blasius boundary layer looks like and what the mean velocity profile of a turbulent boundary layer looks like. Maybe let me show it to you again on the blackboard. Over here. So this, for instance, is a Blasius boundary layer with a certain gradient at the wall, creating a certain shear force. And if we have a turbulent boundary layer, the mean profile looks more like that. Yeah? This is the mean profile. Of course, there are these turbulent fluctuations on top of that. But the mean profile looks like that. And the mean gradient at the wall is a higher gradient. So we have higher shear stress. The mean turbulent shear stresses at the wall are higher for turbulent boundary layers than for laminar boundary layers. Go back. So this is why, in the first place, going beyond this critical Reynolds number, in terms of friction drag, we're increasing the friction drag because we have now a turbulent boundary layer. But there's something else happening, and that's even more important. Look at what happened to the separation point. The separation point here was at 82 degrees, and with the turbulent boundary layer, it's at 125 degrees. So the flow remains attached much longer on the sphere before it separates. That is a bit difficult to explain, and I'm not sure if there's any full rigorous explanation for that, but the phenomenon has been known for a long time, and it's definitely there. So the current understanding or the current explanation for that is that a turbulent boundary layer is more energetic. It has more energy, more momentum in it. You also see this from this fuller from this bigger belly of the velocity profile. There's more energy in it, so it has a tendency to remain attached longer. It takes more to detach it, to separate it from the wake. So this is just a general phenomenon. Turbulent boundary layers are more energetic, stay longer on the surface, separate later. So for flow separation, having turbulence is a good thing. And it's also good for the pressure drag. Because what happens to the wake? The wake has become much smaller. So instead of a huge wake on the left, where the flow separates at 82 degrees, we have now a much smaller wake. Okay, so by going over the critical Reynolds number of 300,000, we obtained a turbulent boundary layer, which increased the friction drag, but we reduced the size of the wake, which reduced the pressure drag. Which one is stronger? Well, because this flow configuration in the first place is a pressure drag dominated configuration, the reduction of the pressure drag counts more. Yes, we lose a bit due to increased friction drag, but overall, we reduce the total drag because we massively reduce the pressure drag. And that phenomenon is known as the drag crisis of a cylinder or of a sphere. It's also happening on a sphere. Let's look at this on the next slide. So what do we see here? This is, I think, a diagram I showed you before in the context of the flow around the cylinder for potential flow. So the potential flow solution is given by the dashed line. Right, that's what we did. I think even almost on the blackboard, we could write down the formula. This is like a sine formula. And we see that the pressure, so here on the ordinate, we have the pressure. On the 0 degree, this is like the leading edge of the cylinder. We have a maximum pressure. That's like the stagnation point on the upstream side. And then as we go to the thickest part of the cylinder, so sideways, we have an accelerated flow. The pressure is reducing. This is the fastest point of the pressure, of the velocity, and so the lowest pressure. And as we go back on the downstream side of the cylinder, the velocities in potential flow decrease again, and we come back to the stagnation point at the downstream. This was potential flow, perfectly symmetric pressure distribution leading to zero drag. Let's look at the thin solid curve. The thin solid curve is what is happening with the laminar boundary layer. Everything looks quite similar here on the upstream side. We have a flow acceleration leading to reduction of the pressure, Bernoulli's law. And here at this point, this is about the 82 degree, the wake starts and the pressure remains more or less constant at the quite a low level. So we have a big area behind the cylinder in the wake with a relatively low pressure. Okay, so we have high pressure from the front and low pressure in the back, creating a lot of pressure drag. The thick solid line is what is happening at Reynolds higher than 300,000. And we see that the flow remains attached until about this point. This is the 125 degrees, or sorry, at this point, it's 125 degrees where the flow then separates. The velocity has already decreased because we're already coming to the back side of the cylinder. The velocity goes down, the pressure increases because the velocity went down, and the separation is only here. So the pressure inside the wake is higher, and it's a smaller wake. So it's two effects. You have a smaller wake, and the pressure inside the wake is higher. So together with the high pressure on the upstream side and the higher pressure in the wake, we have much less drag. The thick solid line is much closer to what we had in potential flow theory, so it's much reduced drag. Jumping from this point to this point happens as we go across a certain critical Reynolds number. And as we go across this line, we say the cylinder or the sphere is going through the drag crisis. And this is shown here in this diagram of the drag coefficient. We had this before, and oops. And we can now assign the thick solid line, which is the very high Reynolds number case beyond the drag crisis, to this region here. And the thin solid line before the drag crisis is associated with this region here. So this is drag coefficient about 1.2. And after this, we have a drag coefficient maybe about 0.4, 0.5. Okay. So it's a weird concept. So we are increasing the velocity a little bit, going beyond the critical Reynolds number, and the drag is dropping. This is the drag crisis. And I think we take a break now, 15-minute break until 1/4 and then we look a bit at what this means and what applications could be of this drag crisis.